Everyone, today we're going to go over PCA, principal component analysis, so the pros and cons of principal component analysis, how it leads to reducing the number of dimensions in your data set while preserving much of the information, as well as some of the advantages, disadvantages, pros and cons, how to mathematically derive PCA and do PCA on a data set. So we're going to go over those details here. Okay, let me just give me 1 second to load up my notes. Okay. So the entire concept of PCA is to reduce the number of dimensions that we have in our data set. So say our data set has like 1,000 dimensions. If we want to preserve the same amount of information with the reduced dimensions with 2 or 3 dimensions, then we can use PCA. So when is PCA useful? So PCA, typically it's used to reduce the number of dimensions in your data set. Numerically, this only works for numerical continuous variables. Dimensionality reduction. Dimensionality reduction. The second problem that PCA fixes is collinearity. So when you have features that are correlated with one another that have and your data set has high collinearity, PCA can produce features that are uncorrelated with one another. So when you have high multicollinearity within the data set, you can use PCA as a tool to resolve that issue. Another thing, another requirement for PCA is PCA is actually very sensitive to outliers. So it's recommended that before using PCA, you check the data set for any outliers, um, because the covariance metric that we use is actually very sensitive to outliers, and that's a lot of the math behind how PCA actually works. PCA is also used for data visualizations, most commonly in 2 or 3 dimensions. So you have a large data set that you want to really understand the structure of the data and capture a lot of the variance. You can do that by using PCA, assuming that it's a numerical data set, continuous data set. You can convert, those, let's say you have 1,000 dimensions in your data. You can use PCA to transform those into 2 or 3 principal components, which then you can easily visualize on a 2D scatter plot or a 3-dimensional plot. Some of the pros of PCA is that it produces uncorrelated independent features. So you can use these features in linear regression on a regression model. It produces uncorrelated features, so it really solves the issues of multicollinearity, as we mentioned before. Correlated features. Some of the cons is that it is sensitive to outliers because of the math behind it, how it uses covariance, how we calculate the eigenvectors, the direction of the variances. So it is very sensitive to outliers. Another con is that there is very little feature interpretability. We are able to calculate these new dimensions, these new principal components, but they don't necessarily mean a lot much in terms of like what they mean in terms of the data. So that's one of the cons, is that there is very little in feature interpretability in this PCA methodology. Also, it is a linear dimensionality reduction. So if you have a data set where the relationship between your variables are actually nonlinear, say they're exponential or they're related by some other function that is nonlinear, then PCA will probably not yield very good results because PCA is a linear dimensionality reduction algorithm. Dimensionality reduction algorithm. So now we're going to go step by step of how PCA works. And one of the reasons that I'm actually doing this is because it's actually very intuitive to understand PCA, and knowing the steps behind mathematically how it is derived helps us to understand the concept of PCA and help us understand what PCA actually does a little bit more. So the first step in principal component analysis is standardization of the data set. By standardizing the data, we make sure that every feature vector in our data set has a mean of 0 and a variance of 1. Every feature vector in our data set. So you can think of this as every column in our data set has mu 0, mean 0, or a standard deviation, not variance, standard deviation of 1. So you can do this by taking each value in the feature vector, subtracting by the mean in the feature vector, divided by the standard deviation of that feature vector. And this will standardize, and you do this for all of the feature vectors in your data set, and this will standardize your data set. So your data set is ready for PCA. The second is to calculate your covariance matrix. Your covariance between X and Y determines the relationship between X and Y. Specifically, it measures how two variables X and Y will vary with one another. X and Y. This is just the formula for covariance over n minus 1. Once we have the covariance matrix, which will calculate the pairwise covariances between the features in the data set, then we calculate what are known as eigenvectors and eigenvalues. Eigenvectors and eigenvalues of the covariance matrix. And eigenvectors, you can think of them as whenever you multiply a matrix by its eigenvector, the transformation that you will get from that vector is only in magnitude. So when you multiply this vector by its matrix, so the eigenvector, when you multiply the matrix by its eigenvector, you will essentially multiply the vector by a scalar value. So for example, let's say this is our matrix. You multiply this matrix by your eigenvector, that will equal to some scalar quantity, some numerical value times the vector. And the change, the factor by which the magnitude of the vector changes, that's what we call the eigenvalue. And the actual vector itself is what we call the eigenvector. And so calculating eigenvectors and eigenvalues represent vectors that we are able to multiply the matrix by and achieve only a change in magnitude instead of direction. So that's the relationship between multiplication of matrices with an eigenvector and how it relates to a scalar multiplication with of the same eigenvector. So now, as we mentioned before, PCA, the reason that we do PCA is to preserve as much variation in the data set while also reducing the number of dimensions in the data set. So how do we calculate how much the cumulative sum of variance that is described upon adding each additional principal component? So the formula for the cumulative sum of variance in the data set that PCA explains is you take the eigenvalue divided by the sum of all the eigenvectors, or of all the eigenvalues. So for the first eigenvector, for the first principal component, you can calculate how much variation that it captures within the data set by looking at the eigenvalue of that eigenvector and dividing that by the sum of all of the eigenvalues of that covariance matrix. And that will give you the proportion of variation in the data set that the first principal component measures. And then if you want to know how much do the first and the second measure, then you can simply do the eigenvector of the second, eigenvalue of the second eigenvector and divide it by the sum of the eigenvalues. So that's the cumulative sum. And the other thing to note is that these eigenvectors that we produce, these are actually loadings, what we call, for the principal components. So this is what we project our original data set onto in order to get our new transformed data set, projecting it onto these new set of axes, these new set of eigenvectors. So you can think of these eigenvectors as if we want to calculate principal component 1. right? We're going to look at the weight one or the loading one or the value in the first or the one of the values in the eigenvectors. You can look at weight one times x1 plus weight two times x2, weight two times x2, and so on. And these are what we call loadings. How do we transform the original data set to get our new principal components? And these are the eigenvectors themselves. Some of the properties of eigenvectors are that the sum of the squared values in any loading or any eigenvector, a loading or eigenvector, is one. Eigenvectors are orthogonal to one another. These loadings are orthogonal to one another. So the dot product of any two loadings or eigenvectors is zero. And that's a reason why they are also uncorrelated and independent. One of the major advantages of principal component analysis is that allows us to use reduced dimensions to perform regression. And one of the advantages of that is now we have independent uncorrelated features in our data set that can better improve the fit of our model. When we do principal component regression, because each principal component is independent of one another, the coefficient estimate, when we fit our regression model with these principal components, the coefficient estimate for each principal component will not change when we add additional principal components. When we add additional principal components. And just another quick fact about principal components. You can create typically P principal components from a P feature data set, but the number of unique and distinct principal components is you can only create a max of the min of n minus 1, P, where n is the number of observations, P is the number of features in your data set, distinct principal components. So this was just a high-level overview trying to simplify the math behind principal component analysis. First step is to standardize your data set. Second step is to find the covariance matrix of your data set. Third is to calculate eigenvectors and eigenvalues of that covariance matrix. The eigenvector, when you multiply a matrix by its eigenvector, you will achieve a transformation that represents only a change in its magnitude, not direction. The change in its magnitude, the factor by which the magnitude changes, is known as the eigenvalue. And though these eigenvectors are known as the loadings or the weights for these different principal components, this is what we transform. These are the new axes for this new feature space that we're projecting the original data set onto. Some of the advantages of principal component analysis, as we mentioned, are that it is a dimensionality reduction algorithm. It can handle high multicollinearity. It's a very good tool for that. Some of the cons are that it is very sensitive to outliers. It has little feature interpretability. It is a linear dimensionality reduction algorithm. And so if your data set has nonlinear relationships, PCA may not be a good fit. So that's PCA in a nutshell. Thank you for watching.